Welcome to the Deep Dive. We get straight to the core insights from your source stack, helping you get informed fast. Today, we're diving into a really big challenge with large language models, how to make them actually run efficiently when dealing with massive amounts of context. Contexts that are way, way longer than just a few pages of text.
Yeah, it's a fundamental problem. These models, they're amazing at handling huge context windows now, like entire books or long, long conversations. But the compute power and the memory needed, they just explode.
Right, the standard transformer architecture kind of hits a wall.
It really does, especially during inference when you're actually using the model.
You mentioned compute. That's the attention mechanism, isn't it? The part that gets really slow.
Exactly. It scales quadratically with the sequence length. So double the context. You're looking at roughly 4 times the computation just for attention. That initial processing of the long prompt, what people call pre-filling it, can get incredibly slow.
And then there's the other side of the coin, memory.
The KV cache. The model has to store these key and value things for every single token it's already seen. And that grows linearly. So more tokens, more memory, simple as that.
The sources gave that really stark example, Llama 3.18b.
Yeah, for 128,000 tokens, which isn't even the theoretical max for some models, it needs over 50 gigabytes of GPU memory just for that cache. That's often just not practical outside huge data centers. It puts a hard limit on things.
So people have obviously been trying to fix this, right? There are ways to speed things up or use less memory.
Oh, absolutely. Lots of clever ideas out there. You've got things like sparse attention-making tokens only pay attention to some other tokens, not the whole sequence.
Okay.
And methods to, just drop parts of that KV cache, throw away stuff the model hopefully doesn't need anymore.
Or even compressing the input before the model sees it.
Exactly. Prompt compression, trying to weed out the unimportant bits of the input prompt itself.
But the sources point out a kind of fundamental weakness in a lot of these approaches.
They do. The core issue is how these methods decide what's important and what's not. Most of them look at the current state, like what the model is attending to right now, based only on the input tokens it's seen so far. Or maybe the attention patterns from the last few generated tokens.
Right. They're guessing future importance based purely on the past or present.
Precisely. And that's often not a reliable guide. The stuff that becomes critical later in the generation, it might not look important initially. You're essentially trying to predict what the model will need without actually knowing what it's going to say next. Flying blind, basically.
Okay. So this is where the big idea in these sources comes in. The real innovation. What if you could get a sneak peek, a cheap preview of what the model might generate, or where its attention might focus in the near future?
And use that peek to make smarter decisions about what to compute or what to keep in memory?
Exactly.
Yeah.
And this involves using those smaller, faster draft models, right? But in a new way.
A fundamentally new way. This is key. We often hear about draft models for speculative decoding.
Yeah, where the little model proposes tokens and the big model checks them super fast. Speeds things up, but the final output is identical. Same total work, just faster.
Right. Speculative decoding is about lossless acceleration. It doesn't change the output distribution, and it doesn't really cut down the total computation or memory the main model uses over the whole sequence.
But this work, it's different.
Completely different goal. The sources frame this as the first work to really leverage draft models for approximate inference. The idea isn't just speed with the same result, it's using the draft model to help the target model make informed approximations.
Approximations that actually reduce the computation and memory needed.
Yes, potentially trading a tiny, tiny bit of output accuracy for significant efficiency gains. That's the novel contribution here.
So our mission today is really to unpack how they do that, this new framework.
Exactly. How does this draft-guided approximation work?
Okay, let's quickly recap the core problems again, just to ground us. We've got that quadratic attention cost slowing down the initial processing, the pre-filling.
Yep.
Painful with long prompts.
And the linear KV cache growth eating GPU memory, that 50 GB example, really sticks. A hard wall for truly long contexts.
And the existing fixes, sparse attention, cache dropping, prompt compression, often struggle because they lack that foresight. They're guessing importance based on limited, backward-looking info.
Right. The sources argue pretty strongly that just looking at initial attention isn't enough to know what's truly vital later on.
Because importance can shift based on what the model is actually generating moment to moment.
So the insight. Use information about future tokens to estimate importance now.
And get that future information cheaply, using a draft model.
How does that work? Why is the draft model's prediction useful?
Well, the core principle is that if the draft model is trained similarly to the target model, maybe it's even distilled from the target model, their behavior tends to align. Their outputs are often similar, and crucially, their internal attention patterns show strong correlation. So the draft model, even though it's smaller and faster, acts like a decent low-cost predictor of what the big model might do or focus on.
Exactly. It's a reliable enough proxy, and this framework leads to two specific techniques they developed, SpecKV and SpecPC.
That KV. That sounds like it's focused on the KV cache.
It is. Speculative KV dropping. It aims to make smarter decisions about dropping KV pairs and also how to do sparse attention during that initial pre-filling phase.
What's wrong with current KV dropping methods, like SnapKV mentioned in the sources?
The main issue is that limited look-back. They might only consider attention patterns from, say, the last few hundred input tokens to decide what's important globally, but that can easily miss something crucial from much earlier in the prompt that only becomes relevant after some generation has happened.
So SpecV uses the draft model's look-ahead. How?
Instead of just using attention calculated from input tokens, SpecV runs the draft model to get some future tokens first. Then, it looks at the attention from those draft output queries back to the original input keys.
Whoa, okay. So it's using the draft's prediction in the future to figure out what was important in the past input.
Essentially, yes. Combined with attention from recent input tokens, it gives a much richer, more forward-looking estimate of importance. Think about that needle in a haystack idea. Find one specific fact in a huge document.
Right.
Methods looking only at the initial input might not see the needle as important right away, but SpecV generates a bit of draft output, maybe the start of an answer referencing the needle. When the attention from that draft output looks back at the input, it lights up the needle tokens much more strongly. The sources have figures showing exactly this.
That makes intuitive sense. The draft gives a hint about where things are going, which helps prioritize the relevant history.
And it's not just intuition, they back it up with theory. Theorem 1 shows the error in SpecV's importance scores is basically proportional to how much the draft's outputs differ from the target's outputs. So if the draft is a good predictor of the target's next tokens, its importance scores for the cache will also be reliable. Gives it a solid mathematical footing.
And the algorithm is pretty neat.
Quite elegant. Step 1. Generate some draft tokens. Step 2. Pass the input and the draft tokens through the target model's attention layers. Step 3. Calculate that cross-attention draft queries looking at input keys. Step 4. Aggregate those scores. Step 5. Use the scores to selectively keep KV pairs or apply structured sparsity during prefill, always keeping the most recent ones too.
Using the draft's future vision to prune the past cache. Got it. Okay, what about the other one? SpecPC, speculative prompt compression.
This one tackles the problem even earlier, compressing the input prompt before the main model even sees most of it.
That sounds like it could save even more less attention work, smaller initial cache.
Potentially, yes. And the way SpecPC uses the draft model is different, maybe even simpler. It doesn't generate draft output. Instead, it just runs the original input prompt through the draft model.
Okay.
And looks at the draft model's own internal attention scores on that input prompt.
So you process the prompt with the cheap model, see where it paid attention, and assume the expensive model will likely pay attention to the same places.
That's the core idea. Again, it relies on that strong correlation observed between draft and target attention patterns. The sources show plots where, yeah, if the draft attends strongly to token X in the input, the target model probably will too. The draft's attention map acts as a low-cost proxy for the target's attention map on the input.
Is there theory for this one too?
Yep, theorems 2 and 3. They actually make a really interesting link to compressed sensing theory. It provides mathematical bounds showing that, under certain conditions, using the draft's attention is a reliable way to approximate the target's attention for the purpose of identifying important tokens. It adds that academic rigor.
So the SpecPC process is feed prompt to draft, get draft's attention scores, aggregate those scores across layers and heads.
Right, maybe weight later tokens more, apply some smoothing or pooling to keep local context.
And then just keep the input tokens with the highest scores, plus a recent window, and feed that compressed prompt to the big model.
Exactly. And a key advantage they highlight is flexibility. Because it operates directly on token attention scores, it doesn't have the constraints some older methods have, like needing sentence boundaries. It can handle messy text, code, even mixed inputs like text and image representations seamlessly.
That's a big deal for real-world use.
Yeah.
Okay, the million-dollar question. Does it actually work? What did the experiments show?
They tested it extensively on benchmarks like Ruler and Longbench, which are specifically designed for long context evaluation. And the results are, well, pretty impressive. Both SpecV and SpecPC consistently outperform the baseline approximation methods in terms of accuracy, especially as the context gets really long.
Better accuracy, and they're supposed to be more efficient.
That's the win, yeah. On Ruler, that needle in a haystack benchmark, SpecPC got up to 25 points higher accuracy than the SnapKV baseline. And SpecPC did incredibly well too, often getting close to the performance of the full target model using the entire prompt, even when SpecPC was compressing it quite heavily. The performance drop-off with length was much gentler.
Wow. And on the more varied long-bench tasks?
Similar story. They really shone on things like few-shot learning and code completion, where pinpointing specific details or understanding longer dependencies is key. That's where the draft's look-ahead seems particularly helpful.
You mentioned something surprising, that SpecPC sometimes did better.
Yeah, that was fascinating. On some tasks, particularly code completion, SpecPC running the target model on a compressed prompt actually beat the target model running on the full original prompt. The thinking is that the compression might sometimes act like a helpful filter, removing noisy or irrelevant parts of the prompt, letting the target model focus better.
So the approximation isn't just efficient. It can sometimes be beneficial for accuracy, too, by reducing noise. What about the speed and memory metrics?
They showed improvements there, too. SpecV with sparse attention reduced the prefill time compared to baseline sparse methods. SpecPC was faster than older prompt compression techniques, despite needing that initial draft model pass. And memory-wise, SpecPC naturally uses less because the target model starts with a smaller, effective prompt.
And using a better draft model helps.
Yes, the ablation studies confirmed that. A higher quality draft generally led to better results for SpecV, reinforcing the idea that it's acting as a proxy, better approximation.
Okay, so let's wrap our heads around the big picture here. The core academic contribution feels really clear now.
It really is. It's about fundamentally rethinking the role of draft models, moving beyond just making exact generation faster to using them as tools to enable principled, efficient approximation within the larger target model, specifically for things like cache management and prompt compression. And they claim to be the first to really formalize and demonstrate this.
Supported by theory and strong empirical results, showing it works better than previous approximate methods.
Exactly. It offers a promising new path for making these incredibly long context models actually practical and efficient.
Did they mention any limitations or next steps?
They did. For SpecV, if the draft generates too many tokens, that adds latency. For SpecPC, just making the draft look ahead much longer didn't automatically translate into huge compression gains, so there's more to explore there.
And future work.
Extending the idea, maybe using look ahead for sparse decoding during generation, or more iterative cache dropping guided by the draft. Lots of possibilities.
What's the key takeaway for you from all this?
For me, it's that paradigm shift. Draft models aren't just accelerators anymore. They're becoming these clever, low-cost simulators or predictors of the big model's internal state and future actions. And we can leverage that prediction specifically to make the big model operate more efficiently through approximation.
Right. So the thought to leave you, the listener, with is this. If these smaller models can act as smart guides, helping massive models approximate effectively on huge contexts, what does that unlock? Does it mean we can finally break through those memory and compute walls for truly enormous sequences? Does it challenge the whole idea that the giant model always needs to process every single piece of information?
It definitely suggests that this kind of intelligent draft-guided approximation might be crucial for making million-token contexts a practical reality, not just a research demo.
Really fascinating developments. That wraps up this deep dive.